Okay, so nearing the end of our P1 videos, we have a section now on earthquakes and waves. Now, earthquakes, as we mentioned in the last video, are caused when two tectonic plates, so these are tectonic plates, so right plates for quickness, rub past each other at a boundary or a fault line. So we can see here that there's two tectonic plates and they're rubbing past each other. Now what happens is they rub past each other, and usually there'll be a little snag somewhere, so maybe a little bit of rock on one side that sticks out that makes this one kind of stop and stick, and then eventually the pressure builds up so much that we get boom, it pushes past, causing a big earthquake as it goes past, because what we get is a big shock here. Now this is called the focus because that's where it actually happens, okay? This is where this little snag is at this focus. If we go directly up from the focus onto the earth here, this point is called the epicenter, and you've probably heard that word before when talking about earthquakes, is the epicenter, the center on the earth where the earthquake actually happens. And earthquakes happen because of waves, okay? An earthquake, this causes shock waves to be sent out in kind of circular waves. You can maybe see really faint circular lines. So it causes shock waves to be sent out around the point of the focus, okay? And these are shock waves here that you feel, and that's what causes the earth to shake. There's two different types of them, but before we know about that, we need to know what a wave actually is, okay? Now, waves are a really big part of physics. There's a lot about them in, they're really, really important, basically. But a wave is simply this. It's a repetitive vibration that transfers energy from place to place without transferring matter. So if you think about, the easiest way to think about waves is a slinky, okay? If you have a slinky and you hold it between two people and one person shakes it up and down, you see a wave passing through that slinky. Now, the wave is transferring movement energy, okay, or energy of sorts, but the matter, so the actual slinky itself, hasn't transferred with it. So once you've passed that wave along, that bit of slinky that you're holding onto doesn't travel back to the other person. It stays where it is. The matter stays where it is, but the movement of that wave carries on. Now, for a real wave, you need to have that repetitively, so it's a repetitive vibration that carries on. And you'll see that with water waves and things like that. The water itself doesn't move, it just moves up and down, but the wave movement moves. Now there's two main types of waves that we need to know about. A transverse wave is what you would usually think of as a wave. Now I'm going to draw these with slinkies, because although for the transverse it's really easy to draw on anyway, without a slinky. For the longitudinal you need that to kind of explain it. So a transverse wave is what you would think of as a normal wave. So it's up and down like this. It looks like a normal wave. Crests and troughs, we'll go on to what they actually are in the next and final video. This is a transverse wave. Now what that means is that the medium, which is the material that is made of, so the slinky here, or the water, if it's a water wave, moves at right angles to the direction of wave travel. So the slinky is moving up and down, okay? This part of the slinky is moving up and down with the wave. The direction of travel, however, the wave itself, this crest, is moving that way. The energy is moving that way. And you can see that that is a right angle between the motion and the wave. So that's what a transverse wave is. Now, examples are, as I've mentioned a few times already, water waves. Most waves, to be honest, are transverse waves. Water waves are one, and the big one is the EM spectrum. So anything in the EM spectrum, so light, radio, gamma, they're all waves, but they're transverse waves. Okay? Now, the second type of wave is a longitudinal wave, and they're much harder to kind of think about or to draw. Now, I want you to imagine holding a slinky between two people and one of you dancing like Beyonce does in Crazy in Love. And what happens is you'll see that your slinky will be nice and far apart at some points, and then it'll bunch up. Then it'll get further and further apart, and it'll bunch up. And it'll get further and further apart, and it'll bunch up. Now this is a longitudinal wave. It's really hard to draw, as you can tell. There's not too many of them around, apart from in earthquakes, in sound, which we'll talk about in a second, and with a slinky. And because of this, I actually call them, because you kind of have to dance like Beyonce to do it, I remember them by saying they're like a Beyonce wave. Okay? So, the difference between these two is that for a transverse wave, we said the direction of wave travel was at right angles to the way the medium moves. Now here, if we look at the medium again, we can see that the medium is moving that way. Yeah, too much orange, I apologise. The medium is moving that way. The wave is also travelling that way. So here, you can do this part, longitudinally move in the same direction. Now, ones we need to know about are the earthquake waves we're going to talk about, but also sound is a longitudinal wave. And that's about it in terms of actual, waves that we see every day. So earthquake waves we'll talk about in a second, and also sound waves. Now, there are two types of waves in an earthquake, and they're called P and S waves. So all earthquakes will have these two types of waves. Now, there's lots of different things that you need to know about them. Firstly, you need to know their names. Now, P just means primary. Okay, a P wave is a primary wave, and an S wave is a secondary wave. But their names can also help you remember, or their initials, what types they are. A P wave is a pressure wave, and an S wave is a shear wave, and what that actually means we'll go on to later on. You might also hear P waves being called compressional waves, but it's the same thing. I like to remember P, pressure, C, S, shear. Transverse or longitudinal. A P wave is a longitudinal wave. Okay, so it moves like a Beyonce slinky wave. Longitudinal. So that kind of thing. An S wave is transverse. So a normal type of wave, and that moves like that. In terms of speed, primary is called a primary wave because it gets there first. P waves are really fast, they're faster. S waves, they're still quite fast, but they're slower than P waves. So primary waves, they're called primary because they're faster, and that means that they get to the surface, arrive at the surface first, because they're primary waves. S waves therefore must arrive second, which is why they're called secondary waves. So there's easy ways to remember these kind of things. Now, primary waves can travel through anything, and this will make more sense in a second when I explain why we need to use these. Primary waves will travel through liquids and solids. However, S waves will only travel through solids. And this is why it's important for us to remember that the mantle is a solid that flows slowly. It's not a liquid. This means, can it travel through the core? Now, the core, remember, if we have a think about how we drew it a few videos back, has got a liquid outer core and a solid inner core. So, a P wave can travel through liquids and solids, so it can travel through the core. An S wave can only travel through solids, so it can't get through that first layer, so it can't travel through the core. Now, that's really important for what we're going to talk about on the next page. But first, we need to think about when you have an earthquake. I don't know if there's been in one, I hope not. The way these waves work, there's my earth. I'm going to draw a nice tall skyscraper building. Imagine it's on its own. And I'm going to say that my earthquake's epicenter is about here. Okay. Now, the first wave to get to the surface is a primary wave. Now, primary waves cause the building, to shake this and that way, okay, side to side. We then get the S waves. I'm going to label that P. Eventually the S wave comes along, and that causes the building to shake up and down. So you get first movement side to side, and then you get up and down movement. And that's why you get also kind of why an earthquake lasts quite a long time, and why you get different types of movement. Now, P and S waves can be really, really important because they can tell us about the structure of the Earth. We can't drill inside the Earth. We can't get that deep. It's too hot. We can get down a few kilometres. We can't get into the centre. Now, we can use P and S waves to help us understand that. I've got here another cross-section of the Earth. I've not put the crust on because the crust is so thin actually here that we don't need to think about it. But I want you to imagine this is a P wave. Now, if I have an earthquake that happens, say, here, now these P waves are going to travel throughout the Earth in all directions, up and down, side to side. There we go, there. Now they're going to travel like this. Oh, sorry, don't want me to move paper. Like this. You can see them avoiding the core because this is the important part. Now a P wave, you just said, can travel through liquid. Now what actually happens is that when it hits a boundary, it does something called refraction that you may have done before, but it travels through the core like this, and then you get ones that refract like that. This is a really bad drawing, I apologise. But you do get P waves going right through the Earth. So P waves can go through all the Earth, go through whole Earth. However, we just said that S waves can't travel through liquids. So if I have my S waves, I have the same earthquake starting here. They can still do this, like that one did. They can still travel anywhere that's a solid. Remember we said that the mantle is a solid. But then they get to here, they can do this one, and do this one. Then they get here, they can't travel through a liquid, so they stop. They get here, they can't travel through a liquid, so they stop. And so S waves can't get to this portion of the Earth, because to do that they have to go through a liquid, and they can't bend their waves, they have to go in a straight line, unless they refract at a boundary. And this causes here something called an S wave shadow, or an S wave shadow zone to be precise. And this is an area where S waves can't reach. Now, this tells us that there must be something liquid in the centre of the Earth. So we know that the core has to have a liquid part. The size of this shadow zone tells us how big the core is. Because if this was smaller, if the core, say if this part was only liquid, then it would be able to get through this bit, and the shadow zone would be smaller, it would be like this. So if this bit, so this is all, you know, an if the outer core was solid, then you'd be able to get things through there, and you'd just get a shadow zone here. So from the size of our shadow zone, we can work out how big the core is, and because S waves can't get through it, but P waves can, we know that it must be liquid. So as you can see, P and S waves, actually, although earthquakes are very destructive, they're really useful sometimes at helping us determine the structure of the Earth. Now, the only thing that's left of P1 is a bit more about waves, and that'll be on the final video, about waves themselves and how to do some calculations with them. So have a look at that if you need some help with that section.